In today's video, we're going to look at two new special types of matrices: row reduced echelon form of a matrix and row echelon form of a matrix. In studying these new forms of a matrix, we're also going to develop techniques for putting any matrix into one of these two forms. I commonly refer to these as operations of a matrix. Specifically, putting a matrix into row echelon form is known as REFing a matrix, and putting a matrix into row reduced echelon form or row reducing a matrix is known as RREFing a matrix. An M by N matrix A is said to be in row reduced echelon form, or RREF, if it satisfies the following three properties. First, all of the zero rows, if there are any, appear at the bottom of the matrix. Second, the first non-zero entry from the left of a non-zero row is a 1. This entry is called the leading one of its row. Third, for each non-zero row, the leading one appears to the right and below any leading ones in preceding rows. Finally, if a column contains a leading 1, then all other entries in that column are 0. If a matrix only satisfies the first three properties, we say that that matrix is in row echelon form. Or REF. So the following three matrices are all in row echelon form, right? Here are the leading ones, right? Notice that each leading one is to the right and below the previous. We have all of our non-zero rows. At the bottom, there are 2. Right? And obviously, they are all leading ones, right? So the first three properties are satisfied. However, the fourth property is not satisfied, right? Because we have a 5 above the 1 here, right? In order for it to be an RREF, this 5 would have to be 0 as well as everything below it. B is also an REF. B also happens to be in RREF, right? But specifically for this example, it is an REF, right? Here's all of the leading non-zero terms. They are indeed all 1s. Right? Every entry below them are 0s, and each leading one appears to the right and below the preceding one. C is also, right? Again, let's circle leading non-zero terms. They are all 1. We have 1 0 row, and that appears at the very bottom. All of the entries below a leading 1 are 0, and all of the leading 1s are to the right and below the preceding leading 1. These three matrices are all in our REF. Right? Again, look at D. D is actually the exact same as B, so there's no need to go over that one again, except to say that not only are the entries below the leading one 0, but so are all the entries above it. Right? Look at E. Again, let's circle the first non-zero entry of each row. They are all 1s. We have 2 0 rows. They appear at the bottom. The leading ones are to the right and below the preceding leading one. Right? All of the entries below the leading ones are 0s. all of the entries above the leading one is 0. Finally, we look at F. First non-zero entries are 1, so they are their leading ones. All entries in the column of a leading 1 are 0. The leading 1 is to the right and below the preceding leading 1. There is a single non-zero row, and it does appear at the bottom. Okay, so an elementary row operation on a matrix A is any one of the following three. We can interchange any two rows. We can multiply a row by a non-zero number. And we can add a multiple of one row to another row. And the question here is, do these look familiar to you? They should. Right? I leave it to the viewer to decide where they look familiar. Finally, we say that an M by N matrix B is said to be row equivalent to an M by N matrix A if B can be produced by applying a finite sequence of elementary row operations to A. Right? So in other words, if you start with a matrix A and you perform a finite number of row operations on it and get a matrix B, those two matrices are said to be row equivalent. Every non-zero M by N matrix A is row equivalent to a matrix in row echelon form. For the proof, what we're going to need to do is we want to show that we can transform A into a matrix in row echelon form only by applying the elementary row operations. And remember, there were three of them. This proof is also going to serve as the method for reducing a matrix into REF. Such a proof is known as a constructive proof because it not only proves the theorem, but it constructs a method of performing the operation mentioned in the theorem. What we do is start by looking in A for the first column with a non-zero entry. Right, so this column is called the pivot column. And the first non-zero entry is called the pivot. All right, so what we want to do is look for the first column that does not have, or that has a non-zero entry in it. Then we're going to look at where that first non-zero entry is. Let's suppose that the pivot column is column J, and the pivot occurs in row I. What we will do is interchange rows 1 and J if necessary. In other words, if the pivot column, I'm sorry, that should not be J. That should be rows 1 and I. In other words, if the pivot occurs in a row other than I, or other than 1, switch row 1 and I, making your pivot now in row 1. This will give us a matrix B, and note, this is important, that the 1J entry of B is guaranteed to not be 0. Right? Because we just made sure that that entry is the pivot, the first non-zero entry. Now, what we do is multiply the first row of B by 1 over B1J. That's why it's important to note that it was non-zero. This will now give us a new matrix. Call it C. And note that this now guarantees that C1J is equal to 1. Now, if B1J is already 1, then this step is not really needed. Now what we do, if CKJ, I'm sorry, that's an H, if CHJ, where H is between 2 and M, is not 0, we want to make it 0. So to do that, add negative CHJ times row 1 to row H. And what we do is do this for every value of H. It then follows that the elements in column J, rows 1, 2, so on and so forth, M of C are now all 0. Denote this matrix D. All right, so summarizing. So far, what we've done is we looked in A for the first column as a non-zero entry. The row where that non-zero entry is located, we switched with row 1. Then we multiplied row 1 by 1 over b1j, guaranteeing that now that first non-zero entry in row 1 is a 1. We then multiplied row 1 by an appropriate constant and added it to each row below it to zero out every single entry below that leading 1. Now we consider the m minus 1 by n matrix, submatrix I should say, submatrix, call it a sub 1 of D, obtained by deleting the first row of D. What we now do is repeat the above procedure. On our matrix A1. Then we will consider a new submatrix by deleting now the first row of our D sub 1, let's call it, and performing the exact same procedure. Continuing in this manner, we obtain a matrix in row echelon form that is row equivalent to our matrix A, and thus the proof is complete. What we will now do is look at an example of taking a matrix and putting it in REF. We will now look at using this method, this algorithm, to put a matrix into REF form. Now, this process is extremely tedious. Good bookkeeping is going to be required for this. While you can do all of this arithmetic in your head, I find it easier to use a calculator to help with this. So we will be making use of the TI Inspire CX2 CAS calculator to aid us in this process. First thing, let's start by rewriting the matrix. Okay, now that we've done that, first thing we want to do is look for the first column that has a non-zero entry. Well, that is column 1. And we want the first row that has a non-zero entry. In other words, what was just circled in blue is our pivot. That is not row 1. So what we want to do is swap row 1 with row 3. Here's where calculus is going to make the bookkeeping a lot simpler. Let's come over to our calculator. All right. First thing we want to do is create the matrix. Let's go Menu, Matrix and Vector, Create a Matrix. Now our matrix had 4 rows and 5 columns. Hit OK. Now let's actually go in and type all of our values in. hit enter. Now the matrix is stored. Now here's what we're going to do. We're swapping row 1 and row 3. Menu, matrix and vector again. We're going to come down here to 9, row operations, and we want to swap rows. Going to hit the arrow key, essentially copy and paste my matrix. Row 3 with row 1, hit enter. And that will be our resulting matrix. And so all we have to do is now copy that matrix into our work. Now we look. That is not a 1, right? It's not a leading 1. So let's go ahead and multiply row 1 by 1/2. Again, we go to Menu, Matrix and Vector, Row Operations. Now we want, number 3, multiply row. What are we multiplying by? 1 over 2. Copy and paste the previous matrix. And what row? 1. Hit enter. That will be our resultant matrix. So again, all we have to do is now copy this into our work. Now the next step is to take a look at column 1, and we want to make every entry aside from that leading 1 0. Well, the good news is row 2 and row 3 is already zeros. All I have to do is make that row 4 a 0, and we can do this by taking -2 times row 1 and adding it to row 4. All right, so in our calculator, again, we want to go to Menu, Matrix and Vector, Row Operations. Now we want this fourth one, multiply row and add. What are we multiplying by? -2. Copy and paste our matrix. We're multiplying row 1 and adding it to row 4. And that would be our resulting matrix. So once again, just copy that into our work. Now remember, what we're doing is at this stage, we are going to eliminate row 1, and we have a new submatrix. So we're going to perform the exact same thing on this submatrix. Right here is our pivot. Right? Now, what I do is I just keep working with the same matrix. I don't rewrite a submatrix, so I'm going to say we will swap row 2 and row 3. What this does is allows me to continue working with the same matrix in this calculator. Now, instead of going through the menu, let's actually type in row swap. Right? If you recall, that was the command. I want the matrix, and it's row 2 with row 3. Notice at this stage, row 1 is going to remain the same throughout the rest of our work. Now, from here I can proceed in two different ways. I can add row 2 to row 4 right away to get rid of that -2 down there. However, I want to stick to the process until we are comfortable with REFing a matrix. So the process says I want to make that 2 a 1. And how is that done? By multiplying row 2 by 1/2. Right? Again, instead of going through the menu, it is just m row, multiply row. That was the command. We're multiplying by 1/2 our matrix, and it's row 2. Now we want to make that -2 in row 4 a 0. How can we do that? Take 2 times row 2 and add it to row 4. Right? The command was m row add. It's 2, the matrix. We're multiplying row 2 and adding to row 4. Right? So what I should have done here is I should have highlighted this, right? Because that's what we're trying to zero out. Right now we're going to again circle our pivot, which is the first 2 in row 3. We want to make that a 1. So to do that, just multiply row 3 by 1/2. And at this stage, both row 1 and row 2 are going to remain the same. Right, now the column that we want to zero out is right here. And again, we're only concerned with zeroing out everything below that leading one. Right, how can we get rid of that 2? Well, we can do -2 row 3 plus row 4. Right, now notice that that final row is all zeros. So there's nothing more that we can do, and we are done. There is our matrix in REF. And these two matrices are row equivalent, right? Because all we did was perform elementary row operations in each step. Every non-zero M by N matrix A is row equivalent to a unique matrix in row reduced echelon form. As with the previous theorem, the proof of this theorem is constructive. That is, this proof is also going to serve as the method of putting a matrix into row reduced echelon form. Unlike REF, the RREF of any matrix is unique, meaning there's only one. When you put a matrix into REF, it is not necessarily unique. A matrix can have several matrices in REF. Now, this unique part is actually quite difficult to prove, so we are not going to prove it in this video. We're only going to develop the method of putting a matrix into RREF. All right, so as before, what we want to show is that we can transform the matrix A into a matrix in RREF only by using the elementary row operations. What we do is we start by proceeding as in Theorem 1. In other words, we will put the matrix into REF first. Right? We obtain, let's call it a matrix H that is in REF. And row equivalent to A. Right, so the first step in this procedure is to use the previous procedure to put it into REF. Now, let's suppose that rows 1, 2, up through R of H are non-zero. And the leading ones in these rows occur in columns C sub 1, C sub 2, so on and so forth, C sub R. Then notice by the previous theorem, we must have that C1 is less than C2, less than so on and so forth, less than CR. Right? This is because that H is in REF already. Now, starting with the last non-zero row of H. In other words, starting with row R, we add suitable multiples of this row to all rows above it to make all entries in column CR above the leading one 0. In other words, in the REF method, we zeroed out every entry below the leading one. Now what we do is we want to zero out all of the entries above each leading one. So starting with the final non-zero row, take that leading one, zero out every entry above it. Then we repeat this process for rows r-1, r-2, so on and so forth, up through the final row 2. Right? So we start at the bottom, zero out every entry above that leading one, move up to the next row, zero out every entry above that leading one, move up to the next row, zero out every entry above that leading one, and we do this until we get to the second row. Right? We zero out then the entry right above that leading one. Okay? Now, there's no need to worry about row 1, right? Because there's no row above it. The result is a matrix K in row-reduced echelon form that has been derived from H by elementary row operations and is thus row equivalent to K. I'm sorry, to H. Now, since A is row equivalent to H, and H is row equivalent to K, we conclude by transitivity that A is row equivalent to K. As was mentioned at the start of the proof of uniqueness is really rather difficult, so it will not be examined. So we're going to say now that this proof is complete. And now this flowchart is kind of a summary of what we just did in the proof. Right? Input the m by n matrix A. Let j equal 1, I equal 1. Is j less than or equal to n? If not, eliminate the entries above the pivots to obtain the RREF of A. If yes, is Aij not equal to 0? If not, is there an AKJ not equal to 0 with k greater than I? All right, so on and so forth, and I will let you read through the rest of this chart on your own. I will scroll slowly. If you need to, go ahead and pause the video at any point so you can read the rest of the flow chart. What we will now do is row reduce a matrix. That is RREFing it, putting it into RREF. Now you should notice that this is the exact same matrix as example number 3. Right, so since we've already put it into REF form, there's no need to repeat that procedure. First thing is, as before, just recopy the matrix. Right, and then by example 3, we had this matrix here. Okay, now from this stage, we go down to the last non-zero row, which in this case is row 3. Look for the leading 1. It's in column 3. What we want to do is zero out every entry above that leading 1. So to do this, I'm going to do 2 at once. Right? Notice if we multiply row 3 by 5 halves and then add it to row 1, we've zeroed out that entry. And if we take negative 3 halves row 3 and add it to row 2, we've zeroed out that entry. So again, I'm going to come over, sorry, wrong screen. I'm going to come over to our calculator. And again, since I'm using the same matrix, I don't need to worry about re-entering a matrix. Right, so we want m row add. Our first one was 5 halves, row 3 plus row 1. Now that would be the result if that was the only step we're doing, but we're not. We're also taking negative 3 halves, row 3, and adding it to row 2. This is going to be our resultant matrix by performing both of those elementary operations simultaneously. So again, we just recopy, or we just copy that resultant matrix. Now that we've done that, we move up to row 2. Column 2 has the leading 1. So we want to zero out the 1 entry that's above it. And that can be done by taking negative 1 times row 2 and adding it to row 1. And once again, just copy the result. All right, we just completed row 2. There's nothing else to do. And there is our matrix in RREF. That concludes today's video on the echelon form of a matrix, putting a matrix into REF and RREF. In the next video, we will take what we just did in this video with what we did in the previous video, putting a linear system as a matrix, combine them, and look at a method for solving systems of linear equations by representing the system as a matrix. This is a much simpler method, in my opinion, to solving particularly complex linear systems than using the method of elimination. So, as always, I thank you for your attention. I hope you enjoyed, and I will see you all in the next video.